So, hi, I'm Manakil, a PhD student at the Center for Quantum Dynamics at Griffith University and part of Eric Street's ion trapping group. So, I'll be presenting our proposed setup for observing Maxwell's demon, a continuation of Liam's talk from Monday. This work is funded in part by Lockheed Martin and the ARC. So basically, we want to demonstrate Maxwell's demon, which would be showing an 100% energetically efficient quantum heat engine, i.e. a memory engine. This would be useful for information and entropy storage and energy efficiency. So as stated throughout the conference, there is this challenge of meeting the growing energy demands by reducing the reliance on fossil fuels and to combat climate change. So I just want to preface this by saying we're not solving the energy issue or creating a magical engine that can immediately be used. We're just trying to prove a concept that can maybe be useful in the future. So heat engines typically use a substance with heat capacity to convert some thermal energy into work while transferring heat to a cooler reservoir. The Stirling engine, for example, operates as a closed cycle system based on the principles of the Carnot engine, theoretically promising high efficiency with limited power output. This is why it finds limited industrial applications and is mostly used for smaller things, apart from some submarines. In contrast, steam engines operate as open cycle systems and have seen broader applications. So here we have the Carnot efficiency, which sets the maximum efficiency that any real heat engine can achieve. The larger the temperature difference, the higher the efficiency. So classical heat engines have this inherent limitation because the second law of thermodynamics dictates that not all the heat taken from a hot reservoir can be converted into work, resulting in some heat being lost to the cold reservoir, making 100% efficiency unattainable. So to minimize waste heat, the QC would need to also be minimized. So everyone knows this. So in the 19th century, James Clerk Maxwell proposed Maxwell's demon thought experiment to show the second law is only a statistical principle that holds almost all the time. In the thought experiment, a hypothetical demon sorts fast and slow-moving particles into separate chambers, seemingly violating the second law by creating a temperature difference without doing work. So you can't have any free lunch. There's no magical way for the demon to operate without adhering to the thermodynamic rules. So since we cannot create a temperature difference without increasing entropy, there must be something missing or misunderstood. So the solution was that the demon's memory incurs an energy cost. This cost dissipates as waste heat during the memory erasure or self-reset, contributing to an overall increase in system entropy, thus maintaining the validity of the second law. So basically our thing is about what if you could have an engine with 100% energy efficiency. So in the thought experiment, we use information about the particles' location to cool them and showing the relationship between energy and information. So by using 2 spin reservoirs and 1 thermal reservoir, we can show close to 100% energy conversion from heat to work without breaking the second law of thermodynamics as we separate heat from the entropy in the heat, the energy from the entropy in the heat. So in a paper by Joan Vaccaro and Stephen Barnett, it was shown that the physical cost of erasing information is related to the type of statistical ensemble used to absorb the entropy of the unwanted information. They also found that by paying the cost in angular momentum or another conserved quantity, the energy cost can be reduced to 0 regardless of temperature. The model being examined employs qubit logic gates, each associated with unique eigenvalues of a conserved quantity other than energy, namely angular momentum. So in Lenge's principle, the energy cost arises from the thermal reservoir, but with this can be substituted with a statistical ensemble of energy degenerate spin half particles, leading to an energy cost in terms of angular momentum rather than heat. So the memory-powered engine can be summed into 3 steps that are shown in the right diagram. So first, the demon has no memory and the gas is in thermal equilibrium. Next, the demon measures the molecule speed, sorting the fast to the right and the slow to the left, then utilizes an engine to extract work from the interaction between the 2 partitions. Finally, the demon's memory is erased using a spin reservoir, and the 2 partitions are allowed to return to equilibrium. So Maxwell's demon extracts work, which is spin labor, from a thermal reservoir, spin therm, using angular momentum as a cost, leading to a higher information entropy, but lower thermodynamic entropy. This spin labor represents the low entropy polarized spin reservoir, while the spin therm signifies the high entropy non-coherent spin reservoir. This cyclic process highlights that there's always a cost, even though it takes a different form. In essence, the engine works by separating the entropy from the heat, eliminating a temperature gradient, so you could have theoretically 100% energy efficiency and pay the cost in information entropy. So this holds significance as it offers a potentially more straightforward method for arranging information storage by filling and erasing memory. Additionally, it's a promising solution for efficient disposal of heat, especially in challenging environments like space with blackbody radiation, for stealth technologies, and in CPU applications. So this was brought up in Liam's talk. So this is related to the can be related to the magnetocaloric effect. However, our approach involves operating near zero magnetic field without inputting work into the system, focusing on converting heat to work rather than work to cooling, and the implementation we're doing will eliminate the reset step that typically involves putting work into the system. So the reason for Lockheed Martin's interest in subsequent funding in this project was their interest in the idea of a coherence capacitor, which they have already patented. The coherence capacitor could, in principle, remove entropy from an amount of heat in the thermal reservoir and turn it into work. So we are an ion trapping group, so we're going to be using ions to demonstrate this, and we plan to use ytterbium-171 ions. The trapped ions are an established quantum system known for its reproducibility with controllable heating and cooling. They also offer precise control and manipulation at the quantum level of all three axes, making them valuable for quantum computing and information processing. So we're going to be using a microfabricated chip trap to combine the ion within the Lambda-Dickey regime with a secular frequency of 1 to 2 megahertz, which is axis dependent. Yeah, this is the ytterbium structure that we're interested in. Yeah, so Raman cooling is a sub-Doppler cooling technique using laser light to cool the ions by transferring energy between the internal levels. Heating is with Stokes Raman cooling, and cooling is with anti-Stokes. So we're going to be using stimulated and spontaneous anti-Stokes Raman cooling to showcase the memory engine with ions releasing photons carrying more energy than the ions' reduced energy state. So sideband cooling manipulates vibrational sidebands by using the lasers to drive the transitions between the vibrational states to get cooling of the ion motion along these vibrational modes through precise frequency tuning. So narrow line width is needed for this high precision in addressing specific quantum states and getting sufficient cooling, hence why our cooling laser is going to be our cooling laser's line width is significantly smaller than the trapping frequency, which means that we can resolve the excitation spectrum. So this is the Maxwell's demon experiment that Liam discussed on Monday, where the ion's internal states and motional modes are coupled, enabling the conversion of thermal motion into higher photon energy. So this will be stimulated Raman cooling, where the detuning is at the gigahertz level. This ion spin serves as the demon's memory, and 2 coherent Raman cooling lasers act as the demon's hands, linking the thermal reservoir to the spin reservoir. The laser's polarization is the spin equivalent of heat, and it's converted into the spin equivalent of work, and it's converted into the spin equivalent of heat, ready to be dumped in the spin reservoir. In this process, entropy decreases in the ion's motion and increases in the ion's spin state, with the ion's thermal energy harnessed and entropy serving as the currency. The memory resets when the photon scatters. So unlike the Maxwell's demon, our setup harvests all the work without relying on a temperature gradient. In essence, this is a proof of concept of demonstrating that a photon entered and emerged with increased thermal energy and that there's tangible evidence of the photon's existence. So for this part of the experiment, we're only doing state detection transfer, not looking at the actual photon energy, which will lead to the next experiment where we're looking at photon energy. So in the experiment, we will employ post-selection as we lack a built-in cavity in the trap, which is essential for non-post-selected measurements. So in this experiment, we're getting the Raman spectrum of a single ytterbium ion via spontaneous anti-Stokes Raman cooling, which in our case is more similar to Doppler cooling with spontaneous emission. So this is to show the efficiency of the work photon in the engine. It's important to note that the emitted photon doesn't always carry more energy. Sometimes it carries less. So there's both heating and cooling, so demons and anti-demons. And to selectively detect these positive work photons, we require a sub-megahertz cavity. We extract the phonon motional heat of the ion into the scattered photon, aiming to observe changes in energy and examine the emitted photons to discern cooling and heating transitions, so the demons and anti-demons, which is why Raman spectroscopy is our method of choice. One of the reasons I said before that we get close to 100% but not actually is that we're limited due to losses from the Zeeman level splitting, where we have some Zeeman contribution to the absorption excitation difference as well as the intended Raman. So our challenge in detecting the minute energy shifts, the 1 to 2 megahertz, resulting from the single scattered photons, requires us to make a cavity with a high absolute transmission and full width half max less than 600 kilohertz, and a finesse greater than 1,000. So we're going to be using near-planar mirrors to offer improved stability, which are needed for maintaining the cavity's length and alignment, which in turn support a high finesse. The slightly curved surfaces reduce the optical aberrations, resulting in a cleaner interference pattern. Moreover, the cavity's ability to support a long range of resonant modes enhances its versatility. Lastly, aligning and maintaining a near-planar Fabry-Perot cavity can be more straightforward compared to cavities featuring strongly curved mirrors such as confocal cavities, which are very annoying to align and seem to not work at high finesse, unless someone can tell me otherwise. So these are the specs and setup for the proposed cavity. The photon light couples from the ion trap will be sigma plus and sigma minus polarizations due to the trap geometry and the single mode fiber coupling. As can be seen, we plan to detect both the transmitted, reflected, and rejected photons to get maximum information. So optical cavities encompass both internal losses and mirror losses, with the reflected signal serving as a diagnostic to determine absorption losses. So while the reflected losses are less commonly calculated, they are of concern for us due to the small input light signals and photons, further reduced by various sources such as coupling, mode matching, absorption loss, light rejection, outcoupling, and intracavity losses. Intracavity losses include the light passing through the cavity and then being reflected out, as well as losses from contaminants on the mirror faces, which affect the finesse. Reflected losses encompass losses from light reflecting off the first mirror and any signal loss due to mirror contamination, while outcoupling losses involve light exiting the cavity and losses due to the contaminants on the second mirror. So in summary, we delved into the understanding of heat engines, con efficiency, and its constraints. We talked about Maxwell's demon and introduced the memory-powered engine and how we're going to be doing it with ion trapping, Raman cooling, and noted the challenges with detecting single photons and the need for a cavity. So yeah, thank you for listening, and thank you to the organizers for putting this all together for the conference. Any questions? Yes.
Really nice, Rose. Thank you. Yeah, any questions?
Can't see.
I've got a quick one. That looked like a lot of crud on your
What?
mirrors. That looked like a lot of crud
Yeah.
in your schematic.
I just assume the worst is going to happen.
Yes.
Yeah, I've had to clean
Dusty
them.
lab.
Yeah, it's more like taking into account everything that could go wrong. Just preparing for it.
Okay.
Okay. And also because it's like single photons, we want to.
So it's pretty.
We want to be able to know where every loss is happening.
Yeah.
We want to know where everything is happening.
Pretty unforgiving. Yeah.
Yeah.